Hello, students. We are going to be working on calculating the area of a region under a curve. And this is one of the main uses of integration. In the first semester, you learned that one of the main uses of finding the derivative was to find the slope of a tangent line to a curve. One of the main uses for integration is to find the area of a region under a curve. We're going to look at the development of that calculation today. So we will first of all start with an underestimate, which you'll see in the figure that I'm pointing to here on the left. And then you'll notice that each one of those rectangles is under the curve, and yet adding together their area would give a close estimate to the actual area. Actual area is being pictured in the middle, and then the overestimate found by rectangles where the height of the rectangle is above the curve, and in those cases, again, gives a close estimate, but not exact. And so what happens with integration, as you find with all things in calculus, that if we would take the limit, making the number of rectangles that are drawn go to infinity, then the underestimate and the overestimate would actually become the area of the region under the curve. So if you can imagine your number of rectangles going to infinity, that makes the width of each rectangle be infinitely small. And in that case, then the estimate would approach and eventually equal the area of the region under the curve. And so we have a definition of the area of a region, and that definition is using the limit process and doing the summation, the limit of the summation from I equals 1 to n of, and then we have this notation here, f of mi times delta x. Now, I will be explaining this to you using a diagram, but for now, I want you to think about the area of a rectangle being found by taking the length times the width. And so you'll see that the explanation that I have right here, the FMI will be the length, only I'm going to call it the height. And this delta X will be the width. And hopefully, as we are going through the lesson, you'll be able to see what I'm talking about with those two symbols. So I have some guidelines for us. The delta X is B minus A over over N, and these two values, F of MI and capital F of MI, are minimums and maximums of the function. Again, stick with me while I explain those in a diagram in just a little bit. You'll see that I have some steps for you to follow, and we will do those steps as we go through our lesson. But probably one of the most important things is how to get started. So this number 2, your A is the left X coordinate, your B is the right X coordinate, and then this delta X is B minus A over N. And then I will explain what we're doing with these things. So let's go ahead and move to the back of your notes. We're going to look at a couple of examples to kind of develop this idea of finding the area under the curve by estimation, and then eventually by doing the limit process. So by estimation, I'm going to have us consider the curve f of x equals negative x squared plus 5. We're going to go from 0 to 2. So let's start thinking about that. Our a is 0. This is 0 right here. Our b is 10/5, this last number right here. And 10 over 5 is just 2. So our a is 0, our b is 2. We have 1, 2, 3, 4, 5 rectangles. So our n is 5, n being the number of rectangles. And our delta x then is, from our formula, b minus a over n. So that would be 2 minus 0 over 5. Well, so 2 minus 0 over 5 is just 2/5. Now, I did that through the use of a formula, but I would like for you to think about this geometrically. So the distance from 0 to this first line is 2/5. And then from 2/5 to 4/5 is 2/5, and 2/5 for each one of these. So this 2/5 is just the distance between each one of these hash marks, and those are representative of where each rectangle is drawn. So your delta x is nothing more than the width of each one of those rectangles, okay? And then we need to know something about the height of each one of these rectangles. So the height of each one, now I want you to be paying attention to where the rectangles are drawn. So notice that this first rectangle, the right end point of this vertex is actually on the curve. And because I chose a function that continually decreases, that is actually the case for each one of these rectangles. The right end point is on the curve. So if I wanted to know how tall that number 1 rectangle is, it would be whatever the y value of this ordered pair on the corner would be. And that y value could be found by doing f of this 2/5. So the height of this first rectangle is f of 2/5. And I could plug 2/5 into my original problem, do negative 2/5 squared, add 5, and I would know how tall that first rectangle is. Likewise, my second rectangle is f of 4/5, because it is whatever that y value is for the ordered pair. And then f of 6/5, and so on, and so on, and so on. So my next one would be f of 8/5, and then f of 10/5, or f of 2. All right. So if I wanted to make that a more general statement rather than having each individual height, I could think about how to describe that height using my function notation. So this is where we're going to start thinking about a summation formula. And I'm going to use an I as a counter. So the height of each one of these rectangles would be f of, now obviously the 2/5 is involved. So the question is, what do I have to do to that 2/5 so that I can represent each one of these values? Well, if I take, in this first one, 2/5 times 1, I would get 2/5. In the second one, if I took 2/5 times 2, I would get 4/5. Likewise, 2/5 times 3 to get 6/5. 2/5 times 4 to get 8/5, and 2/5 times 5 to get 10/5, or 2. So in other words, my counter, I'll use an I. If I went from 1 to 2 to 3 to 4 to 5 and multiplied that by my 2/5, I would be able to, in a general form, state the height of any one of those rectangles. So the height of each rectangle can be represented by f of 2/5 I. So now I have a representation. I have the height, and I said before, our width we calculated using the delta x. So the delta x, which was equal to 2/5, is the width of each one of these rectangles. So now we're going to calculate the area. And so the area is equal to the sum. So now we're going to use this summation symbol. And it is from I, this is my counter, equals 1 to 5 of, now I need my length, which in this case is the height. So f of 2/5 I. I'll make that look a little bit better. F of 2/5 I times my width, 2/5. So I have my height, which is length, times my width, 2/5. And so now I can calculate this area. Again, it is the sum from I equals 1 to 5. And again, my 1 to 5, 5 is my number of rectangles. Now, f of 2/5 I simply means that I am going to be using the function notation, putting 2/5 I in for the x. So notice that the negative is not being squared. So it's negative, and then 2/5 I would replace your x. That gets squared, and then we add 5. Now, that's the f of 2/5 I. And then I have to take that times 2/5. All right, now, this is where you are going to need to learn how your calculator does this summation formula. At the top of these notes, I have written down the keystrokes that are used for the TI-83. Now, this is a probably an older version than what some of you have. You can also do this calculation on Desmos. So I'm going to switch over to Desmos and show you the calculation on there. And then we'll come. All right, so I've got Desmos going, and to get the summation, you'll need to find the keyboard and go to Functions. So you're in Functions, the summation symbol. Now, it naturally comes up with n equals. We used an I, so you can change this to an I. I know that with the TI, they tend to stick with X's, so whatever your variable requirements are, you do need to be consistent. So we're going I equals 1, and then at the top it's 5. So this is telling you 1, 2, 3, 4, 5 will be your counter. Then you'll just put in your function. So now I'm going to start it with the negative and then the parentheses. It was 2/5 I, and close that parentheses. We had to square that and then add 5. Now, notice that that gives me an answer, but remember, that was just the height of each rectangle. And then I'm going to need to go back and put a parentheses around all of that because I have to multiply all of that by the width of each rectangle, which was 2/5. And so notice that I get an answer of 6.48, and that would be the estimated area under the curve using the 5 rectangles. Now, I had to clear my screen, but I'm going to bring up my completed notes so that you can see what that is. So we used a calculator right here, and we found 6.48 as the estimated area using the right endpoint of each one of the rectangles. So now I'm going to continue on. I'm going to take it back to this screen, and we're going to look at the other diagram. Now for that diagram, we have rectangles where instead of the right endpoint being on the curve, each one of the rectangles is drawn so that the left endpoint of each rectangle is on the curve. So the left endpoint of each rectangle is going to tell us how high each rectangle is. So we still have the same information as far as the width is concerned. This still has a delta x of 2/5. But the height, although each one of these rectangles is going to be based on this function, I can't say that this first rectangle is f of 2/5 because it's not. This one is actually f of whatever is going on when x is a 0. So it's f of 0. Then my next one is f of 2/5. And then my next one is f of 4/5. And then f of 6/5. And finally f of 8/5. So essentially, what I did was I backed up 1 unit for each one of these. And so on my counter, let's think about what I could use in order to make a general statement for this. So again, I'm going to be using f of, and I'm going to be using that 2/5 somehow. But I need my counter to be backed up 1 from where I was last time. So last time I used an I. So let's use I minus 1 as my counter. And let's just see if this works. So if I is a 1, that will be 1 minus 1, which is 0, and I'll get f of 0. If I is a 2, I'll have 2 minus 1. That will be a 1, and I'll get f of 2/5. If I is 3, so notice I'm just going up by 1, I'll get 3 minus 1, that's a 2. 2 times 2/5, there's my 4/5. 4 minus 1 would give me 3, there's my 6/5. And again, 5 minus 1, so my last rectangle, 5 minus 1 would be 4 times 2, 8/5. So this could be my general statement of the height of each one of these rectangles. And so the area under the curve can be found by doing the summation from I equals 1 to 5. And again, that 5 is coming from my number of rectangles. And instead of doing f of 2/5 I, this time I'll do f of 2/5 times I minus 1. And that will be the height of each one of those rectangles, because each one of those rectangles has the left endpoint on the curve and not the right endpoint. So we had to back up 1. And remember, that's the height. We have to take this times the width of 2/5. So once again, we'll substitute that into our equation. So it's I equals 1 to 5. Our equation, remember, is negative x squared plus 5. So we'll have negative and then our x squared. Now, I think I'm going to go ahead and distribute the 2/5. So 2/5 I minus 2/5. That's going to be my x value. So this is my negative x. That gets squared. Then add 5. And I'm going to take all of that times 2/5. So I have my height times my width. And once again, I want you to be able to use a calculator to get this area approximation. I'll show it to you on Desmos. I've got that pulled up now, so we should be able to do the calculation. And actually, I can just modify the one that I already have, which is kind of a nice thing about Desmos. So I need the 2/5 I minus 2/5. And essentially, that lets you see that we backed up 1 width. You can kind of see that that happened there. And that was an easy fix, because here's my estimate, 8.08. So the approximate area, 8.08. And so now I'm going to switch back to my completed notes, because I'd like for you to see. I'm going to get rid of my ink on here. I wanted you to see that second estimate giving me 8.08. So I now have what we would call a lower sum, a lower estimate. I have an upper sum, an upper estimate, and the actual area is between those two estimates. So if I were to use 10 rectangles, I would have gotten an even closer estimate, or 20 rectangles, even closer. An infinitely number of rectangles, I would have actually gotten the exact area under the curve. And so that's what we're shooting for, is eventually to do a limit process and get the exact area under the curve. So hopefully this explanation lets you see where some of the formulas came from that I was referencing on this first page. So for example, the delta x being b minus a over n. Hopefully that makes sense, that if you take the left minus the right and divide by your number of rectangles, you would find the width of each one of the rectangles. And then this m plus a times I, or a plus I minus 1 times delta x, that's just telling you whether you are using a left endpoint or a right endpoint for your rectangle. Rather than having to draw it out, you've got a couple of little formulas here that'll let you know, do I need to back up 1, or do I need to just stay right on each one of the hash marks? And then for number 5, we just did an estimate where we knew the number of rectangles. And so notice we did a summation and we used a calculator. We're going to do one more example of that, kind of following this process. And then I'm going to have you use the limit process where we do not know the number of rectangles, but yet we calculate the area under the curve. So your second example, you can see the completed notes. I'm going to try to do this one for us in the video. Hopefully I can write well enough that you can see what's going on. So to get started on this, I think one of the first things that you need to take into account would be the A and the B. So A is your leftmost X, and so that's going to be a 0. The B is the rightmost X, so that would be this right here. So B is a 2, and your delta X, or excuse me, let's get the delta X. So delta X is B minus A over your number of rectangles. So I need to know that. My number of rectangles, if I count them up, I have 8. So it's B minus A over your number of rectangles, and that makes delta X be 2/8 or 1/4. And so hopefully that makes sense. 1/4, 2/4, 3/4, 4/4 would be 1. So your width of each rectangle is going to be 1/4. All right, now you are asked to find both an upper and a lower sum. And at this point, you might not know which one is which. So instead of calling it an upper and a lower sum, we're just going to refer to these as right endpoints and left endpoints. So for the right endpoints, we will use, and I'm going to go ahead and call it what I called it on your setup. We will use MI as A plus I times delta X. And you'll see what happens with this. So that would be your A, which in this case is 0, plus, and then your delta X, which was 1/4, and then I. Well, if you think about that, that's just 1/4 I. Very similar to what we reasoned about with our first example, where the height of each rectangle could have been generalized to 2/4 I. So in this case, the height of each rectangle could be generalized to 1/4 I. And I could have just said I times delta X, but not every time is your A, is your beginning X, a 0. So you have to take that into account. So you do need this little formula using the A, because your starting point is not always 0. But once you know this value, then you're going to do a summation. So the area is equal to the sum from I equals 1 to your number of rectangles. That would be 8. And then it's F of what we got for the MI. So F of 1/4 I. Remember, think of this as length times width. So you've got your length or your height. You have to multiply that by the width, which was 1/4. All right, so our area is going to be the sum from I equals 1 to 8. And now you look for what is the function. The function is y equals the square root of x and then plus 2. So you're going to do the square root of 1/4 I and then have plus 2. Remember that that's the f of x, and then times the delta x 1/4. And then this is where you use your calculator. Now, I'm not going to take video time to do that anymore. I am going to spell calculator correctly. So you would need to make sure that you practice with whatever calculator you're going to use and do that summation with the calculator and be very thankful that you get to use one. And you get 6.038. Without a calculator, this would take some tedious work. So your area approximation using the right endpoints is 6.038. And then we will switch to the left endpoints. And again, notice that I'm not concerning myself with whether I have just found an upper or a lower estimate. I'm just going to find both estimates, one using the right and one using the left. For the left endpoints, my MI is going to be found by doing A plus, and then instead of just I have to back it up one, so I minus 1 times my delta x. So A was a 0, and again, you have to take into account A because it is not always 0. Plus, and then I'll have I minus 1 times my 1/4. And so as I simplify this, I will end up with 1/4 I minus 1/4. And so that is what I substitute in as I do my, area approximation. So area is going to equal the sum from I equals 1 to 8 of f of 1/4 I minus 1/4, and then times my delta x, which was 1/4. So again, you get the idea of the length times the width. And so substituting into our formula, that would be the sum from I equals 1 to 8 of the square root. Now we have to put 1/4 I minus 1/4 inside the square root. Then add 2. Don't forget to do that because all of that's part of your formula. And then times the width of 1/4. And you use your calculator again, and you should get your area approximation to be 5.685. Now, obviously, that number is smaller. You might take a look at your diagram, and hopefully it makes sense to you that the left endpoints, I'm going to highlight those in green, the rectangles that are drawn using the left endpoints do underestimate that curve. And the rectangles made using the right endpoints, so those are those overestimators. That would be this one and this one. And notice that you do have rectangles in here that I'm using twice. So and then I think yes, and then that would be it here. So I have 1, 2, 3, 4, 5, 6, 7, 8. I have 8 blue marks. I had 8 green marks for my different rectangles that were being used. And you can see that over and underestimation hopefully taking place. So the actual area is going to be trapped in between 5.685 and 6.038. And so we could write that using an inequality for the actual area. And so this is what we do when we do numerical approximation using right endpoints and left endpoints. And I will tell you that you may just be asked to find an approximation, but not both the upper and the lower sum. So if that is the case, then by all means use the easier formula, the one for the right endpoints. So if you're not asked to find both the right and the left, then use the MI that is found by just doing A plus I times delta X. It's not necessary to do both on all of them unless it says to find both the lower and the upper sum. All right, I will do a separate video for the limit process. So you'll want to be sure that you follow along that when you do those limit problems.